Okay, converting 35 centimeters to meters, that's going to be 0.35 meters. Converting 87 grams to kilograms will be 0.087 kilograms. Multiplying 3.8 times 10 to the 14th times 5.1 times 10 to the 12th. Okay, well, let's look at online calculator here. And I forget what the numbers are. 3.8, 5.1. So I just type in here. 3.8 times 5.1 equals 19.38. So 1.938 times 10 to the 47th. Please type that into your calculator and make sure that you can get the exact same thing. That's 1.9. Now this 1.9 isn't exactly what I had on the online calculator. The online calculator said 19.38, but I moved it an extra decimal point so that I end up with a number here between 0 and 10. And I adjusted this accordingly. When you type this into your calculator with the proper scientific notation, you will get this answer right here. So if you have a TI calculator, it'll be 3.8, and then the second function, and then the number or the button right above the 7 button, which says EE, and then you'll type in 14. And then you type in times 5.1, second function, EE, the number or the button right above the 7, 32, and then you press equals and you should get this over here. If you don't, please be sure that you talk to your teacher about it. Now, 3 ways that it might be displayed on your calculator. It could be 1.938E with a 47, or maybe it has it without the E, just a space, or maybe it has a little tiny times 10 there. What does it mean if the variable is directly proportional to X? That means that any percent change in X leads to the same change in Y. So if X increases by 50%, Y will increase by 50%. If X decreases by 33%, Y will decrease by 33%. Number 5, go ahead and pause the video for a moment and read the situation in number 5. So is this considered a valid scientific argument? Or is it a red herring? Or is it ad hominem attack? Or is it an appeal to force? And the answer is, it's an appeal to force. Odie, no. Sorry, I had to scold my dog there for a second. It's an appeal to force. It says you must agree with me, otherwise I'm going to hurt you by taking away your career. Okay, spend a moment reading the main ideas from the last lesson. And then read today's purpose, relevance, success, and the grades and the quiz. New notes. Newton's second law is F equals ma. where F is the net force. I want to make sure it's the net force. You have to add all the forces together in one way or the other, using Pythagorean theorem perhaps, or other fancy math. M is going to be the mass, and that needs to be in kilograms, please. A is the acceleration, and every time you see acceleration in this class, it's going to be meters per second squared. So number one, what force gets a 200 kilogram bicyclist to accelerate at 3 meters per second? Put in 200 kilograms for the M. Put in 3 meters per second squared for the A. And we get 200 times 3, which is 600. That's the easy part. But what about the units? I have kilograms, and I have meters, and I have seconds squared. Nothing cancels out, and so everything just stays in its place. We have kilograms times meters divided by seconds squared. Now that's a mouthful. So scientists have abbreviated that, and they call it the Newton, which is abbreviated as capital N, honoring Mr. Isaac Newton, who came up with the idea of this equation at least. So what acceleration will a 150 Newton force give to a 25 kilogram object? Start off with Newton's second law, F equals ma. We're going to put in 150 in for the F. 25 kilograms is the M. And then we have the unknown A. So to figure this out, we divide both sides by 25. And we find out then that A is equal to 6. Now it's acceleration, and so the unit for acceleration in this class is always meters per second squared. Number 3, what's the relationship between net force and acceleration? So we have this equation F equals ma. And if we want, we could put this over 1, and we could put this over 1. And so that just makes it more obvious a proportion, 2 fractions equal to each other. And we see that the net force F and the acceleration A are both on the top of these fractions. And so that means that it is a direct proportion. Any percent change in A will lead to the exact same percent change in F. So if A increases by 25%, F has to increase by 25%. If F decreases by 10%, then the acceleration will decrease by 10%. Number 4, the force on an object is increased 7 times, but the mass remains the same. What happens to the acceleration? Okay, so look at this. It says mass remains the same. So we're talking about the exact same object or very, very similar objects. So if I have a car and I make the engine push on that car 7 times stronger than a moment before, then the acceleration should increase by 7 times. In other words, increase by 700%. Number 5, if you want to triple the acceleration of an object, what has to happen to the applied force? The acceleration and the force are directly proportional. So whatever happens to the acceleration has to happen to the force. It triples as well. Number 6, the net force on an 8 kilogram object is decreased by 50%. what happens to the acceleration? Force and acceleration are directly proportional. Whatever happens to the net force happens to the acceleration, and so the acceleration decreases by 50%. If you push on an object half as hard, it's going to accelerate half as much. Number 7, rewrite F equals ma so that it is a proportion with m on opposite sides, m and a on opposite sides of the equal sign. It's going to look like that. What is the relationship between mass and acceleration? Well, we can see here that mass is on the bottom and acceleration is on the top. They are on opposite sides of the fraction bars, and so therefore they change in opposite ways. If m decreases by 50%, then a increases by 50%. Now, why would that be? You think about it. You have a force on a certain truck, and let's say the truck has its bed full of big rocks. And so the engine can make that truck accelerate at a certain rate. It's going to be a little bit slower than normal because it has such a heavy load. The mass of the truck and rocks is so big that the engine can't accelerate very much. However, if you decrease the mass of the whole situation, you dump off some of the rocks, the mass goes down, but that enables the acceleration to go up. It can accelerate faster now that it has a lighter load. So that's what we mean by an inverse relationship. They change in opposite ways. Number 8, the mass of an object decreases to be 1/4 of its original mass. Now that means that it was divided by 4. Okay, the force remains the same. What happens to the acceleration? So mass and acceleration are inverse proportions. So whatever happens to one, the opposite thing happens to the other. So if the mass is divided by 4, that means that the acceleration is going to be multiplied by 4. Number 9, you push on a wagon that has just a little bit of dirt in it, and you see its acceleration. What happens to the acceleration if you put more dirt in it and you quadruple the whole mass? Okay, quadrupling the mass means that the mass is multiplied by 4. So that means it gets heavier and heavier. It's harder to push. The acceleration is going to be divided by 4. It changes in the opposite direction. Mass and acceleration are inversely related. Opposite things happen. Number 10, why do babies need a 5-point seatbelt while adults don't? Okay, so if we look at an adult and a baby in a crash. So here we have the baby in the seat, little car seat, and then we have the big adult. The big adult in a crash will have, well, let's say it's a mild fender bender. Somebody rear ends this blue car with the adult and the baby in it. The adult, with their big mass, might be thrown forward just a little bit, but the seatbelt holds them in just fine. So they don't have a great acceleration by being rear-ended. But the baby has a much smaller mass. Well, mass and acceleration are opposites. So if you have a smaller mass, you're going to have a bigger acceleration. The baby's head and body is going to have a larger acceleration forward. And so we have the 5-point seatbelt to hold them in more securely. The 5-point seatbelt, that's like what we have in race car drivers, where you have the straps above both shoulders, straps about both hips, and then the strap between the legs. 5 different places where you have straps. Okay, the tablecloth trick demonstrates the second law. If you go ahead and look at the embedded video, you'll see the tablecloth trick where people pull a tablecloth out from underneath the plates and glasses. That is not a myth. That is not something that is only seen in cartoons, but that actually is real. So go ahead and stop the video and watch that. Okay, I assume that you have now watched the video, and to explain it a little bit more, here we go with applying Newton's second law to the tablecloth trick. We're applying the idea of F equals ma. So if we have a very little force of friction on between the tablecloth and the plates, that means it will have a very small acceleration of the plates. And so you want to use a very smooth tablecloth. Let's see here. The force of say that again. The mass and the acceleration are inverse. And so if we have a very, very big mass, then we'll have very small accelerations. And so that's why they want to fill up the glasses with water to increase the mass. And that will decrease the acceleration as you pull out the tablecloth. There are some other things as well about the trick, but those are the major ones. Okay, net forces. Newton's second law is about net forces causing accelerations. To see if an object accelerates or not, you must combine all the forces and see if they cancel out. If there is no net force, then there must be no acceleration. Mistake alert. Please note that this statement just relates to net forces and acceleration, as in F equals ma. The force here is the net force. It does not relate to net forces to velocity. It does not say if there's no net force, there must be no velocity. No. That is false. It says if there's no net force, then there's no change in velocity. Change in velocity is acceleration. It can still be moving. It's just not changing its motion. Consider these two situations. Letter A. There can be zero net force if the object is stationary. If it's just sitting there and sitting there and sitting there, then the acceleration is zero. And when we say F equals ma, we say F equals some mass times zero. If it's just sitting there, there's no acceleration. And it doesn't matter then what you multiply zero by, whatever the mass is, we're going to get the force is zero. So whenever you have an object stationary, that automatically means that there is zero net force. There might be 2 or 3 or 4 forces that act on the object at the very same time and cancel out. It's just that the net force is zero. Let's look at the second statement, statement B. There can be zero net force when the object is moving steadily. So imagine a train track. And imagine a train traveling on this. Oh. If the train is moving at a steady velocity, let's say positive 55 miles per hour. If it is traveling at that constant speed, then it is not accelerating. There's no acceleration. If there is no acceleration, there is no net force. But you might be thinking to yourself, hey, there's the force of the motor. The motor is pushing that way. So there isn't that. No, no, no. There is the force of friction that is going to balance it out. The force of friction and the force of the motor will be exactly equal. They will cancel out, no net force, and you will have a steady velocity of 55 miles per hour. Number 11, an object is not accelerating. So that means it's either stationary or maybe it's moving at constant speed. We don't know which. We just know that it's not accelerating. What do we know about the net forces on it? If A is 0, then to find the force, we multiply the mass times the acceleration, which is 0. So that means that the force must be 0. If it's not accelerating, meaning it's either stationary or it's moving at constant speed, either way, the force, the net force, must be 0. All the forces acting on it cancel out. Number 12, try the opposite idea. If an object has no net forces acting on it, what's the acceleration? Well, again, F equals ma. If the force is 0, there's going to be some kind of a mass. What does the A have to be? M times what is 0? Well, the A has got to be 0. Draw a force diagram for the following objects. A person sitting on the floor. Okay, we're going to draw them sitting crisscross applesauce. Well, we have the force of gravity pulling down on them. But at the very same time, we have the force of the floor pushing up. So there are forces acting on the person, but since they're just sitting there, they are not accelerating upwards or downwards or left or right or forward or back. That must mean that these two forces are equal and opposite. They cancel out. And so I draw the two arrows to be exactly the same length. That means that they are the same strength, and since they're in opposite directions, they will cancel out. Okay, letter B, a car going steadily down the road. So there's the car and it's moving to the right. We know there are lots of forces acting on this thing. There's the force of the motor going forward. But there'll be the force of friction pushing back. Since the car is not speeding up or slowing down, that means that these two forces have got to be equal and opposite. And so I draw them the same length. But it's more than that. We have the force of gravity pulling down, and we have the force of the road pushing up. Those two blue arrows are the same length to represent the idea that these two forces are equal but opposite, so they cancel out. The car is not accelerating upwards like a helicopter. It's not accelerating downwards like a submarine. It is staying steady going down the road, and so these are showing equal and opposite, canceling out. No net force up and down, so no acceleration up and down. Okay, now letter C, a car going faster and faster. This is different than the previous problem. If it's getting faster and faster, That means that it is accelerating. So there is a net force. We're going to have the force of the motor pushing harder than the force of friction. And so I draw the arrows different lengths. The force of the motor being the stronger one to make the car faster and faster, that's going to be longer than the force of friction pushing backwards. Okay, a car slowing down. In this case, the force pushing backwards is going to be stronger than the force pushing forwards. And so therefore the car slows down. And the backwards push is the force of friction. And the forward force is the force of the motor. But the friction is bigger. And so it's going to slow the car down. Number 14, remember that velocity has speed and direction. If you change direction, you are changing velocity, and therefore you have some kind of an acceleration. If an object keeps the same speed but changes direction, there must be a net force pushing on it. So if you think about a car taking a curve, and I'm just going to draw a block for the car, an overhead view. The car does not turn automatically. There has to be some kind of a force, and that's going to be the force of friction between the turned wheels and the road. If you remove that friction, let's say with an icy road, ice has no friction, the car is going to go just keep on going straight and end up going into the ditch. You have to have that friction that pushes it. And in the same way, you have to turn the tires with the steering wheel, and that will create this extra friction. If you don't turn the tires, you're not going to have the friction, you're not going to turn. So once again, I'm just trying to get to the idea that you have to have a force to change the speed or direction of the car. This force that changes the direction will result in what we call an acceleration, even though the speedometer will read the same thing. It is still a change in direction. Okay, that's the end of the notes. We are in the year 2020. We're not doing the lab, so you don't have to worry about that. But in other years, 2021 or even further out into the future, you may have done the lab in the previous class time. If you haven't finished that, please do so now. And then we'll have an assignment in Schoology. I believe it's on the shorter side. In 2020, it's only about 6 questions long, I believe. Don't forget the wrap-ups.